Welcome to the deep dive. Today, we're really getting into it, cracking open the source material you've given us.
Yeah, the training session stuff, basics of angles.
Exactly. And for someone like you, an electrical engineer who really gets the nuts and bolts, our mission is to, well, go beyond just definitions.
Right.
We want to unpack these foundational concepts, the different angles, why they are so critical, absolutely vital for power system operation, and how they're monitored.
It's fundamental stuff, but the implications are huge.
Definitely. We're aiming to reveal some maybe surprising insights hidden in what might seem like, basic concepts. It's about the unseen forces.
Absolutely. Angles sound simple, maybe day one material, but in a complex grid, they're profoundly important. It's how the grid communicates its health, really.
Okay, let's dive in. Let's unpack it. The source material, it zeroes in on three main angles we need to grasp.
First one, phase angle. Usually you see it as theta.
Theta, right?
Now, think of this like a snapshot. Just one single location, one node on the grid. It's the angular separation, the difference in, let's say, phase or timing between the voltage waveform and the current waveform. But critically, at that specific point.
So it's literally measuring how much the current is like ahead of the voltage or behind it.
Exactly, as those waves cycle.
Yeah.
Measured from that zero crossing, the reference point on the horizontal axis.
Got it.
And for this measurement to actually mean anything practical, you absolutely have to be measuring voltage and current at the same node.
Makes sense.
And they must be at the same frequency. That's non-negotiable.
Okay. And this is where we get into leading and lagging, isn't it? Like capacitive loads make the current lead the voltage.
So right, capacitors tend to inject reactive power, pushing that current waveform slightly ahead in time.
And inductive loads do the opposite. They make the current lag behind the voltage. Thinking motors, transformers, that kind of thing.
Precisely. Inductive loads consume reactive power. And here's where it gets, well, really interesting connecting it back to the physics. Yeah. It's leading or lagging. It is the direct result of reactance. The opposition that capacitors and inductors put up.
Not like resistance.
Exactly. Resistance opposes current in phase. Reactance opposes it by shifting the phase relative to the voltage.
So inductive reactance causes the lag?
And capacitive reactance causes the lead.
Yeah.
And if you had a purely inductive or purely capacitive circuit, you'd see exactly 90 degrees phase shift.
Right, that classic 90 degrees. Okay, so it's the reactance driving that VI angle separation. Now, the source also mentioned another definition for phase angle, something about power.
Ah, yes, the angle between active power, MW, and complex power, MVA.
That sounds different. How does that connect?
Well, it's maybe different terminology, but it's fundamentally the same angle, just viewed through the lens of power instead of waveforms. Think back to the power triangle.
Okay, yeah. Active, reactive, apparent power.
Exactly. You've got active power, MW, on one side, the real workhorse, reactive power, MVAR, on the other, supporting fields, charging lines, and complex power, MVA, as the hypotenuse, the total power.
Right.
The angle in that triangle between the active power leg, MW, and the hypotenuse, MVA, is the exact same angle as the phase difference between voltage and current at that point.
It's just trigonometry.
It is. The cosine of that VI phase angle, that is the power factor, which is MW divided by MVA. So whether you look at the VNI waveforms or the power components, you're dealing with the same fundamental relationship at that single location.
Okay, that connects the dots nicely. So phase angle, local VA thing, or MW MVA thing.
Got it.
What's angle number 2?
Next up is the torque angle, sometimes called the load angle, usually delta.
Delta, okay.
Now, this isn't about a point on the wire anymore. This is about what's happening inside a rotating synchronous machine.
You mean like a big generator? Or a synchronous motor?
Exactly those. It's the angular separation between the magnetic field created by the rotor.
The spinning part.
Right, driven by the turbine in a generator or pulling the shaft in a motor.
Right.
And the magnetic field created by the stator windings, the stationary part.
Okay, rotor field versus stator field.
Yeah. And the source is specific here. It's the angle between the rotating magnetic field, the MMFs.
Magnetomotive force.
Right, MMFs from the rotor and stator. It sort of ignores tiny effects like voltage drop across resistance or armature leakage flux.
Okay, so focusing on the core magnetic interaction. In a generator, then.
In a generator, the rotor spins at synchronous speed. Its magnetic field basically drags the stator's magnetic field along, inducing voltage. But the stator field actually lags behind the rotor field just a bit.
It can't quite keep up.
Sort of. And that angular lag, that's your delta. That is the load angle. And here's the really critical piece. The amount of real power the generator's actually producing and sending out. It's directly proportional to the sine of this load angle.
Side of delta, so bigger angle, more power, up to a point, I assume.
Exactly. Up to its stability limit, yes. More angle means it's working harder.
And for a synchronous motor, similar idea, but it's called torque angle.
Yet analogous concept. The stator field rotates, pulling the rotor's field along, making the shaft turn. The rotor field lags behind the stator field. That difference is the torque angle, and the torque the motor develops is proportional to the sine of that angle.
So this angle really matters when you're talking about the machines themselves, generators at the utility, big industrial motors.
Precisely. It's internal to the machine's operation.
Okay, so we've got phase angle, local VI, load torque angle, internal machine rotor stator. What's the third one?
The third crucial one is the power angle. This one shifts our perspective again. It's the angular separation, the phase difference between the voltages at two different points. Any two adjacent nodes, usually in the power system.
Okay, wait. Phase angle was V versus I at one node. Load angle was rotor versus stator field in one machine. Power angle is V at node A versus V at node B.
You got it. It's the angle between two locations on the grid, specifically the difference in their voltage phase angles.
And why is that one so important?
Well, arguably, it's the most fundamental for understanding how power moves around the whole system. Because this angle, it dictates the direction of active power flow. Active power, MW, naturally wants to flow from the node with the higher power angle.
To the node with the lower power angle, like
Right.
water flowing downhill.
Exactly. It's the electrical potential gradient, so to speak, for active power. It tells the MW where to go.
And the amount of power flowing between those 2 points, also related to this angle.
Yes. Assuming the voltage magnitudes are reasonably stable, the active power transfer between two adjacent nodes is proportional to the sine of this power angle between them.
Huh. So, similar to the generator's load angle determining its output, the power angle between buses determines the flow between them.
Precisely. And this helps explain something else the source mentioned. For a generator, its internal load angle, that rotor versus stator thing, effectively sets the phase angle of its voltage at its terminals relative to the rest of the system. So when you measure the angle between the generator's terminal voltage and the voltage at the bus it's connected to, that difference is essentially its load angle showing up externally.
So for a generator, its power angle relative to the next bus is its load angle.
Practically speaking, yes. They are the same thing in that context.
That makes a lot more sense. The internal angle becomes the external angle difference. So power angle is key for transmission lines, understanding flow.
Yeah, absolutely crucial. And while we touched on MW and MVAR before, MW being active power, MVAR, reactive power, the power angle is the main driver for active power flow. Reactive power flow is generally more sensitive to differences in voltage magnitude between buses.
Okay, 3 angles. Phase, load torque, power. Distinct, but clearly related. So why, beyond just defining them, are they so incredibly vital for actually operating a power system day to day?
Because, well, they're the vital signs. They're the core indicators of the system's health, its performance, its stability. They aren't just numbers in a textbook. They're what engineers and operators are constantly watching and managing. Yep. The source really highlights their key roles. It says the power angle is critical for the overall stability of the power system. Can the grid ride through a disturbance? Power angle tells you a lot about that.
And the phase angle, you link that to power factor.
Exactly. Phase angle is key for managing power factor locally, which in turn is all about managing reactive power compensation efficiently. If your power factor is poor, you're pushing too much total current, MVA, for the useful MW you're delivering. That means higher losses. Managing phase angle helps optimize that.
Makes sense. And the load torque angle.
That one's vital for the stability of individual generators and big motors. If a generator's load angle swings too far, gets too large, it loses synchronism with the grid, trips offline, big problem. Same idea for motor torque angle.
So putting it all together, understanding and controlling these angles is fundamental. It's about keeping the grid efficient, stable, and secure.
Couldn't say it better.
Yeah.
They're the parameters operators use to gauge system stress, balance, and how close things might be to the edge of instability.
Which leads perfectly into the practical side. How do we actually see these angles? How does monitoring work?
Monitoring. It's everything in operations. It gives engineers, operators that real-time view they desperately need. Better monitoring means better control.
Sure.
It means enhanced security for the whole system. It allows them to make adjustments, maybe change generation or line flows when there's a disturbance. And critically, it ensures we're operating within safe limits, not pushing things too far.
And the source seemed to really emphasize power angle monitoring specifically for system operation.
It does,
Yeah.
and rightly so. because power angle speaks directly to system-wide stability, those potentially dangerous inter-area oscillations. The source describes two main types of power angle monitoring:
Okay.
adjacent node angle monitoring and wide area node pair angle monitoring.
Let's start with adjacent node angle. Sounds like points right next to each other.
Exactly. It's the voltage angular difference between nodes that are directly connected. Think the two ends of a transmission line, for instance. This one is absolutely critical for local system stability,
Why local?
because a smaller angle between directly connected points means there's stronger synchronizing torque between them. That's the electrical force pulling generators or sections of the grid together, keeping them locked in step.
So smaller angle means they're more tightly coupled, electrically speaking, less likely to swing apart.
Precisely. So its importance in both system operation and planning is huge. It's a key indicator for the stability of, say, a radio connection, one line feeding a whole area.
Right.
It's essential when you need to reclose a breaker after a fault, bring a line back online. You have to check that angle. If it's too big when you close, you get a massive power surge, potentially damaging equipment or causing instability.
Wow. Okay.
So it helps define safe synchronization limits, tells you your stability margins locally.
And in planning, do they have targets for this?
Yeah, the source mentions rules of thumb used in planning, like designing the system so that adjacent angles normally stay below, say, 30 degrees.
Yeah.
That provides a good stability margin. Planners use this when they study N1 conditions. What happens if we lose one critical line? They need to ensure the angles on the remaining adjacent paths don't shoot up past stability limits. It's about meeting both thermal limits, how much current a line can carry, and stability limits, how much angle it can sustain.
Got it. Adjacent nodes equals local stability. Synchronizing torque, keeping things below 30 degrees is good. What about the other type, wide area node pair angle?
Right. This is looking at the angular separation between nodes that are much farther apart, maybe geographically or just electrically distant, across different control areas perhaps.
They're not directly connected.
Usually not. This angle is less about that direct local synchronizing force and more about assessing the overall stress level across a larger part of the system. It's used to look for potential inter-area oscillations where whole regions might swing against each other. It helps monitor for potentially problematic power flows across large distances. Sometimes these wide area angle differences are used to define flow gates, which are basically limits on how much power can be transferred across certain boundaries in the grid.
Now, the source made a point here. Unlike the adjacent angle having that 30-degree guideline, there are no specific thumb rule limits for these wide area angles. Why not?
Yeah, that's a really crucial difference. Adjacent angles, they directly relate to that physical synchronizing force between 2 points, and that force has real limits as the angle gets bigger, approaching 90 degrees where it starts to weaken significantly.
Okay.
Wide area angles, though, they aren't usually measuring a direct synchronizing link between those specific far apart points. They're more like an indicator of the overall condition.
Yeah.
Think system stress, maybe voltage profile issues across the region, or those slow inter-area oscillation modes.
So less of a hard limit, more of a trend to watch?
Exactly. Operators use them to see how the system is behaving overall. They set thresholds, sure, but it's more about interpretation. For instance, a really high wide area angle might suggest there's a huge amount of power being pushed across the transmission paths connecting those areas. Could mean lines are heavily loaded, maybe voltage support is weak somewhere in between.
And low angles could mean something else.
Low wide area angles can also indicate issues, yeah, often related to voltage levels or unusual power flow patterns. It's about understanding the context.
Makes sense. Adjacent is about the direct connection strength. Wide area is about the bigger picture stress. So how are these actually measured? What technologies are involved?
Good question. The source breaks it down. You've got your offline study methods first. Things like load flow analysis, transient stability simulations. Engineers use these all the time for planning, for what-if studies.
But for running the grid now, you need real time.
Absolutely. You need online field measurements.
Yeah.
And the source splits these into two camps, asynchronous and time synchronized.
Okay, asynchronous first.
Right. Asynchronous methods include things like a local phase angle transducer right there in the substation measuring the angle. Or, more broadly, estimates that come from the state estimator in the main control center.
The state estimator, what's that?
It's a complex piece of software. It takes all the regular SCADA measurements, voltage, current, power flows from various points across the grid, which arrive at slightly different times.
Because SCADA isn't perfectly synchronized.
Exactly. And it runs calculations to figure out the most likely consistent state of the entire grid at that moment. including the estimated voltage magnitudes and, crucially, the angles at all the major buses. It's vital. It gives operators their main overview, but its data rate is pretty slow. Maybe one update every minute or even every 5 minutes.
Slow.
And the key weakness for angle monitoring, the input data it uses, and therefore its output, is not time synchronized across locations. Each measurement has its own timestamp, but they aren't aligned to one universal clock.
And that was a big hurdle for really understanding wide area dynamics, wasn't it?
A massive hurdle. You just couldn't get a true simultaneous snapshot of what all the angles were doing across a huge grid at the exact same instant. Imagine trying to compare the angle in, say, California with the angle in New York. If the measurements were taken even seconds apart during a disturbance, the comparison could be meaningless.
Yeah, you'd have alignment nightmares.
Totally. You had issues with too much data, maybe, bandwidth, storage, but the killer was the lack of a common time reference. You couldn't reliably compare phase angles measured hundreds or thousands of miles apart. You knew what was happening locally, or you had this calculated estimate based on delayed, unsynchronized data, but you couldn't see the real-time dynamics.
Especially fast stuff, like oscillations.
Exactly, which is why this limitation drove the need for a better way. The fundamental solution. Establish a common reference signal for estimating phasors that's voltage magnitude and angle across different locations, all at the exact same time.
And the source points to GPS as the key.
Yes. GPS provides an incredibly precise, universal time signal available practically anywhere. So substations equipped with the right gear can use this GPS signal to get a perfectly synchronized timestamp, like setting T0 everywhere simultaneously.
Okay.
This allows devices at different substations to sample the AC waveform's voltage and current within the exact same, very short time window. Then, by processing those perfectly synchronized samples, they can calculate the phasor representation, the magnitude, and, critically, the angle, all relative to that common GPS time reference.
And that is the magic behind synchrophasor technology, PMUs.
That's it, precisely. Synchrophasors, or phasor measurement units, PMUs, are the devices that do this. They form the backbone of wide area monitoring systems, or WAMS.
WAMS, heard that acronym?
Because they use that common timestamp, the angle measured by a PMU in Florida can be directly compared meaningfully to the angle from a PMU in Washington State, because they represent the exact same instant in time.
That's a game changer.
Absolutely. It gives operators and engineers an unprecedented high-fidelity view of the grid's dynamic angular behavior and the data rate. Way faster than the state estimator. We're talking 25, 50, even 100 samples per second.
Wow. Compared to once a minute.
Right. It lets you see oscillations, angle swings, dynamic events happening in almost real time that were completely invisible before with just SCADA and state estimation. It fundamentally changed how we can monitor and manage stability across large interconnections.
It really sounds like moving from, I don't know, looking at individual photos taken at different times to watching a perfectly synchronized high-speed video of the entire grid's electrical heartbeat.
That's a great analogy, from static estimation to dynamic observation. Huge leap.
Okay, the source also provided some interesting perspectives how different roles view these angles. How does a grid operator's focus differ from, say, a system planner's?
Yeah, very different viewpoints based on their jobs. The grid operator. They're in the control room, managing the system right now.
Boots on the ground, electrically speaking.
Exactly. Their mantra, according to the source, is know your angle control stability margin. They're using the tools. They have a state estimator, WAMS data from PMUs, to do angular baselining. What do angles normally look like?
Establish the norm.
Right. Then they look for deviations, sudden changes, trends that signal stress or some kind of event. They might use offline load flow studies to understand angular sensitivity, what happens if this line trips.
And they have those caution limits you mentioned for adjacent angles?
Definitely. Keep an eye out if an adjacent angle goes over 20 degrees normally, or maybe 30 degrees if a key line is already out and one condition.
Yeah.
And extreme caution, like flashing red lights, if the maximum angular separation anywhere in their control area exceeds 90 degrees. That's a huge sign of stress, potential instability.
So they use the monitoring to pinpoint critical angles to watch closely.
Absolutely. Both adjacent and wide area. They figure out, okay, which angle pairs are most sensitive? Which ones tell us the most? They also actively investigate how to reduce angles if needed, maybe by shifting generation or changing the network topology, especially if they need to close a breaker safely across a high angle.
And they feed info back to the planners.
Crucial feedback loop. And they rely on automation too. Things like remote synchronization systems that use these angle measurements to safely reconnect parts of the grid.
And those wide area angles, they're interpreting that data constantly.
All the time. What does it mean if the maximum separation hits 100 degrees during peak load? Okay, that probably indicates stress. Maybe some areas are weakly connected. They learn to recognize signatures. What does a drop in a certain wide area angle mean? Maybe less power is flowing, or maybe voltage is improved somewhere. They set alarms. Alert me if angle XY goes above 90 degrees, signaling they might need to take action, like calling for more reactive support or curtailing a transfer. They see how everyday things, load changes, generation shifts, ripple through the angles across their entire region.
Okay, that's the operator immediate control real-time interpretation. What about the system planner, longer view?
Much longer view. Their focus is more like, know your angle control stability margin and ensure we have enough redundancy to meet reliability criteria under all sorts of varying conditions.
Building robustness for the future.
Exactly. They use angle stability studies extensively when evaluating projects.
Yep.
New transmission lines, new power plants, large new loads. How will these affect angular stability? They scrutinize radial connections. They study extreme scenarios. What if this major tie line between regions suddenly trips? Will the system hold together? Will angles go crazy?
And they need good models for this.
Very detailed, validated models, incorporating all the generator controls, the protection systems, and critically, they take that feedback from the grid operators very seriously. What angles are actually causing issues in real operation? Where are the weak points showing up? Their goal is to design a future grid that can withstand the expected stresses, with angles being a primary metric for stability.
Okay, so just to quickly recap that summary table from the source. Phase angle.
Mainly about local power factor, reactive power. Important locally, but not usually a major focus for the main control center.
Load torque angle.
That's about the stability of the individual generator or motor. Again, vital for the plant operator. But the angle value itself isn't typically monitored centrally. Its consequences are, though.
Right. But power angle, that's the big one for the system view.
That's the one. All about overall system stability. To really see it properly, especially wide area, you need that time-synchronized data.
From WAMS, from PMUs.
Exactly. And because it tells you about power flow direction, system stress, stability margins, it is highly significant for the central control center operators and planners.
This has been a fantastic deep dive, really taking concepts that might seem basic on the surface and showing just how critical they are and how sophisticated the management and monitoring it's become. Understanding phase, load torque, and power angles, it really is fundamental to grasping how power flows and how stability is maintained.
It really is.
Yeah.
And seeing that evolution in monitoring, especially the jump we got from time-synchronized measurements with synchrophasers, it really highlights how technology has to keep pace with grid complexity.
Absolutely. Which, makes you think. So here's a final thought, maybe a provocative one for you, the electrical engineer listening in. We've seen how vital these angles are and how technology like synchrophasers revolutionized our ability to see and manage them dynamically across huge distances. What's the next major leap needed?
Good question.
With renewables, storage, electric vehicles, all making the grid faster, more complex, more dynamic, what technological advancements or maybe operational strategies building on this foundation of real-time synchronized angled data are most urgently needed now to keep enhancing reliability and security? What comes after WAMS as we know it?
That's the multi-billion-dollar question, isn't it? The challenge is definitely growing, and the need for even smarter, faster ways to understand and manage these angles is only going up.
Indeed. And hey, this was just session 1 from that training material. Your deep dive continues.
Actually, digging into power system stability itself should be interesting.
Do come back for new videos on power system.